Hi guys. So we are going to be talking about rates of change in this set of notes, which we've been talking about a lot recently anyway. We just haven't been using those specific words. So let's go back and review average rate of change and instantaneous rate of change. All right, so average rate of change, remember that's going to be calculating basically the slope between 2 points. So I'm going to draw point A and a point B. And to calculate that average rate of change, it's going to be the change in the y values over the change in the x values. Or in this case, it'd be, if this is called the function f, it'd be f of b minus f of a all over b minus a. Again, since that is a slope, I'm talking about the slope of the secant line specifically for this. So we're going to write that down, that visually. This is the slope of the secant line. Connecting the points A f of a and B f of b. All right, so then there's instantaneous rate of change. So we are looking for the slope at a specific point. That looks pretty bad. Hold on 1 second. Yeah, the slope at a specific point. Remember, the slope of that tangent line, we can call that f prime of a. Or remember our other notation, that would be df dx at x, or the derivative of s with respect to x at x equals a. We can find that 2 different ways other than just calculating the slope of that tangent line. If we have the function itself, we can take the limit of the difference quotient. As h approaches 0. Or we could take the limit of the average rate of change. As x approaches a. All right, and then let's write down again visually, this is the slope of the tangent line at x equals a. Okay, so key things to remember, you know that you're going to calculate the average rate of change. One, obviously, if you see the word average in the word problem, or if you see 2 coordinates or 2 pieces of time, 2 pieces of information. You would know that you're looking for the instantaneous rate of change if you are given information about a single point of time or just a single piece of information. No matter what, you're going to see the word change or you're going to see the word rate. It's just 1 piece of information or 2 that really is going to tell you. All right, so practice 1, it says the table below contains data of the temperature T on the surface of Mars at Martian time T, collected by the NASA Pathfinder space probe. Part A, calculate the average change in temperature from 6:11 a.m. to 9:02. So other than it saying average, I do see that I'm looking at a range of times. So clearly I'm going to calculate the average rate of change. So change in temperature over change in time. All right, I am going to go with, let's see, would it be easier to do 6:11 minus 9:05 or 9:05 minus 6:11? later time minus earlier time. And their temperatures would be negative 44.3 degrees Celsius minus negative 71.6 degrees Celsius. And I'm just going to remind you a few times throughout the video, if you need to pause this to go ahead and think about the information and try the problems on your own before you just want to hear me talk, go ahead and do that. I think it'd be better for you to pause and try comprehending than just to listen to me do all of this. All right, so let's go ahead and, whoa, there we go. I'm going to go ahead and subtract those temperatures. All right, 27.3. As far as the time goes, let's see, I'm going to count up from 6:11. So 6:11, 7:11, 8:11. I'm not going to go to 9:11, otherwise I'd pass up 9:05. So that's 2 hours. All right. Let's see, to get to 9 a.m., that's going to be, I can do mental math, 49 minutes, right? This is kind of embarrassing. Yeah. So 49 minutes to get to 9 a.m. plus 5, 54. Because I have hours and minutes here, I'm going to actually divide the 50 by 60 to turn that into hours. Or I'm sorry, 54 divided by 60. All right, so that would be 0.9. So I'm looking at 2.9 hours. And I'm going to take the 27.3 degrees Celsius and divide the 2.9. All right, 9.41. We'll take it out to 3, 414. Use the proper label, degrees Celsius per hour. So just kind of thinking about what the question was asking. The average change in temperature on Mars from 6:11 a.m. to 9:05 p.m. was 9.414 degrees Celsius per hour. Okay. Part B, use the graph to estimate the change in temperature at a single time. I'm looking for the instantaneous rate of change. Now, remember, there's a few ways that we can get that instantaneous rate of change. We could, one, take the derivative of our function t at 12:28 p.m. But we don't know the function. We have the graph. We don't know the function. So we are actually going to have to visualize the derivative, i.e. the slope of the tangent line. So I'm still calculating slope here, but it's up the tangent line this time, not a secant line. And the nice thing about this problem is that there's already a second coordinate plotted up there for us. So we can just go ahead and use the first coordinate for the 1228 and that coordinate A for the other point on the tangent line. All right, same process as last time. So I'm going to suggest that you just pause the video, try it, see if you get the same answer as me, because I'm just going to have my work up here in 3, 2, 1. All right, so there we have it. The change in temperature at exactly 12:28 p.m. was 3.616 degrees Celsius per hour. If you have questions on practice one, if anything didn't make sense, make sure that you go ahead and write that down and ask me in class. Let's go to the next example. All right, the area of the circle is given by the equation A equals pi r squared. Compute the change in area with respect to the radius when the radius is 2 and the radius is 5. Now, notice it's not talking about the average change in area over that entire radius change interval. It's asking us to calculate the change in area at 2 times or at 2 radii, but they're basically individual problems. Calculate the change in area with respect to radius when radius equals 2. Calculate the change in area with respect to the radius when radius equals 5. So we're going to calculate individually those instantaneous rates of change. So I'm going to write my area formula down just one more time. Not that I have to. And if I am looking at finding the instantaneous rate of change, remember that is the slope of the secant line. I'm tangent line, but I'm not looking at a graph. I have a function. I could just take the derivative. And spitting that out loud, derivative of the area with respect to radius. So r is my variable there. I'm just going to take the derivative of r squared like I normally would. Pi is just a coefficient. So power rule, take that 2, multiply by it, subtract the power down by 1. Do we recognize the formula 2 pi r? That is the formula for the circumference of a circle. Okay, so we were asked to find the change in radius or the change in area when the radius was 2. And unfortunately, they did not give us labels, so we're not going to label this. But it would be some unit squared. Oh, no. The area would have been some unit squared. The label would just be this the individual unit. Okay, so the second question in this says, which is larger and why? Well, obviously 10 pi is larger than 4 pi, but let's think about why. The area is changing. So when your radius is larger, you have a larger surface area to work with for all of those, I guess the entire surface to expand to a larger area. So I know that sounds a little circular of some reasoning, but I'm going to say there's more surface area to expand when the radius is bigger. Okay. Next practice. I would say make sure that you have room for enough writing. I'll write down all the time intervals. That way you can figure out if your spacing is going to work. It says use the position graph to answer the following questions. Note that the y-axis measures the car's distance from the starting point. Describe the car's motion, both speed and position, over the time from 0 hours to 5 hours. So we have some pretty natural breaks here. 0 to 1, 1 to 2, 2 to 3, 3 to like 3.2, 3.2 to 3.8, 3.8 to 4.1, and then 4.1 to, I would say, about 4.6. So I'm going to write all of those little intervals up. That way you can kind of figure out how much spacing you need when you're writing all this up. Maybe I don't have enough space. All right, give me a moment. It'll appear now. Okay, so going from 0 to 1, the position is getting larger, so it's getting further away from its starting point. So I'm going to say that it's moving forward. And then it looks like we are speeding up. There's a few reasons I know that. One, it looks like, hold on. Oh, that's not what I wanted to do. I want to erase. So it looks like it started off changing its speed a little bit more slowly, and then you can kind of see that it's getting faster there, or it's not moving as slowly as like this first portion. The other way that I know that is because the slopes of those are going to be the slopes at those individual points. Those are going to be the rates of change. And remember, the velocity is the change in position over change in time. I see that those slopes are getting steeper, so it means that I'm moving faster. And I do highly suggest that you pause this and kind of double check every interval as I go. Don't wait until the very end, but just every single interval I do, pause it and see if that you can figure out the position and the speed. All right, so from 0 to 2, my position is still getting larger, so I'm still moving forward. But let's talk about the slopes here. Large slope, smaller slope, smaller slope. So I am slowing down. Or you can tell that I'm covering a little less distance over time as I get closer and closer to 2. All right, 2 to 3, the position, it's stuck at like 160. It's not moving anywhere that entire time. So I'm going to say that I'm staying still or that the car is stopped. All right, 3 to 3.2. So I'm looking at this section right here. So I kind of have two things going on. It looks like I'm starting off speeding up, but then it looks like I start slowing down. So really all I can say about that interval is that I'm moving forward and then I'm going from speeding up to slowing down. Because right at 3.2, can you tell me what's happening? Looks like I'm changing direction from, instead of moving forward, to moving backwards, which I can tell because I was at a further position and then I moved to a smaller position closer to home after that section. So we can kind of kill both of these at once. Moving forward from 3 to 3.2. And speeding up to slowing down. pretty much the exact opposite for 3-2 to 3-8. Moving backwards. Like I said, that position is going from a higher amount to a smaller amount. And I'm going to say that I am, well, it looks like this is a lot steeper than it is down there. So I am actually still speeding up to slowing down, which I hope would make sense. If you're turning around on that backwards portion, when you are actually fully turned around, you're going to speed up. And then when we come to this flat spot later, you have to slow down to stop your position essentially. So even those are negative, think about the values of those, really steep to less steep. Ignore the negative. All right, so again, we talked about that next section a little bit, that flat portion. The position is staying still for a little bit of time, not moving anywhere, staying still, car stopped. All right, and final section. Again, moving forward, my position goes from smaller to larger. And then look at the slopes of those tangent lines. Looks like I'm moving faster, I'm speeding up, which realistically doesn't make sense for this to be the end of the graph, because you do eventually have to stop. So I would have expected to see it slowing down and coming to its final resting place. But it looks like we don't have the full picture of what the graph is. So we'll just stop at the speeding up part. Okay, let's move on to part B. Was the car's average velocity greater over the first 2 hours or the last 2 hours? So average velocity, again, that's going to measure the change in position over the change in time, which we can visualize by looking at the slope of the secant line over those 2 hour intervals. All right, so first 2 hours, we are looking at here to here. Second or last 2 hours, here to, let's see, 2.6 here. All right, definitely have a much faster average velocity over those first 2 hours, just looking at the slope that is so much larger. But also we're covering a lot more distance over the same amount of time. Like the first 2 hours, that's covering about 160 kilometers over 2 hours, whereas the last two, what is that? Like roughly not even 75, or like just 60. So let's write up our answer. I can get it to pop up. There we go. I'm going to say the car's average velocity is greater over the first 2 hours than the last two, because the car traveled further over the same period of time. And then we can also mention that the slope of the secant line is much greater over those first 2 hours. So I'm going to pause it and you'll see the answer pop up now. Okay, so let's talk about linear motion in general, now that we've gone through an example with it. So your position, we're going to be working with a lot of position functions coming up soon. So it's really important to remember that the position function is going to measure the distance from the starting position, which means that you can have positive positions and you can also have negative positions. So if you're forward or to the right, it'll be positive. If you're moving backwards or to the left, it's going to be negative. Okay. Velocity. So it depends on what kind of velocity we're talking about. We're talking about average velocity, just like average rate of change. That is going to be more specifically the change in position over the change in time, which we can visualize by looking at the slope of the secant line. The instantaneous velocity, or more commonly referred to as just velocity, that instead is going to be called v of t, or instead of delta s over delta t, ds dt, or we could say s prime of t. Remember, that is instead the slope of the tangent line. You can also tell that you're being asked about the instantaneous velocity if you are asked what is the rate of change in position with respect to time. Whenever you hear that word with respect, that should be a cue that you're talking about derivatives. Also a cue if it's talking about just one time and not an interval of times. Okay. If your velocity is positive, that means that you or the object is moving forward. If the velocity is negative, the object is moving backwards. And if you think back to when we were doing the position graph a moment ago, all of the times that we saw that the car was moving backwards, like when that position was going from a further one to a smaller one, those slopes of the tangent lines were negative. When the velocity is 0, we're not moving. Or we could be momentarily at a velocity of 0 where we're turning around. And then throw back here, the absolute value of the velocity is the speed. Speed, just looking at how fast I'm going, I don't care what direction I'm moving. All right, hold on.